Alright, we're going to begin section 14.5 in this video, which is triple integrals in cylindrical coordinates. So we learned section 14.1 was double integrals, and then 14.2 we did double integrals in polar coordinates. So this is kind of the analog to polar coordinates, but for triple integrals. So first off, let's just start with a set of coordinate axes to kind of orient ourselves. All right, so say we have some point in 3 dimensions, and we'll put our point right here. I'm not going to label that point anything yet. So usually that would have coordinates x, y, and z. When we work in cylindrical coordinates instead, we talk about r, theta, and z. So the first part of cylindrical coordinates that we'll talk about is just basically polar coordinates in the xy plane, and then after using polar coordinates in the xy plane, you just go up or down directly above whatever your point was that you're considering in polar coordinates in the xy plane. So for this point right here, for instance, we'll say, okay, well, how far out from the origin is this? And we'll put a dotted line coming down here. And then a dotted line from the origin to right there. So this distance, how far out from the origin in the xy plane, is that, and that distance r is in the xy plane. Then what is this angle theta that this dotted line makes with the positive x-axis? So we'll call that theta. So remember, this dotted line down here and this angle right here, those are both in the xy plane. And then after that, we have this point and we go up z units. So in cylindrical coordinates, this is not x, y, z, it's r, theta, z. So that's how we determine a point in cylindrical coordinates. So it would be natural for us to want to go back and forth between cylindrical and rectangular coordinates. So to do that, to convert from cylindrical coordinates r, theta, z to rectangular coordinates, x, y, z, we use x equals r cosine theta, y equals r sine theta, and z equals z. So the assumption here, we're starting with r theta z. So given you have all three of those, you plug what you have into the right hand side to get whatever you want in rectangular coordinates. So we take our r and theta, put them in there, we'll get our x, r and theta, we get our y, the z we had here, so the z is going to be the same. So now say you want to go from rectangular to cylindrical. So to convert from rectangular coordinates x, y, z, to cylindrical coordinates, r theta z, we use r squared equals x squared plus y squared, tangent of theta equals y over x, and z equals z. So given your x and your y, put them in here to get your r squared, and then whatever you have to do, of course, either trigonometry or algebra. Same thing, put your y and x in here, get your theta, and your z is going to be the same thing. All right, and also I'm going to just point you to some equations and figures in your textbook, so you can see some equations that they already have set up, some familiar equations from rectangular coordinates that now have been set up in cylindrical coordinates, as well as some graphs. So C table 14.1 and figure 14.6 on page 938. So all the things that they do there, we're familiar with them in rectangular coordinates. So we could just take and use these formulas to switch them to cylindrical coordinates, but they kind of set a few of them up for us in the textbook. All right, so now how do we set up a triple integral in cylindrical coordinates? We're basically going to combine our knowledge of the double integral in polar coordinates with our general knowledge of triple integrals, and that's how we'll set up an integral. Triple integrals in cylindrical coordinates. So the triple integral over region D of f of x, y, z dv equals the iterated integral from alpha to beta, and then from h sub 1 of theta to h sub 2 of theta. And then so these two outside integrals, that's exactly what we had from polar coordinates. And the inside integral is what we had from triple integrals in general, so f1 and f2. But it was before f1 was a function of two variables. So say for instance, f would be a function of x and y, which is normally what we would see it. So it would be f1 of xy. But that's not the case here, because we don't want to work with x and y at all, because we don't have any x's or y's that we're going to be using when we switch to this. So all of those x, y's, and z's are going to get switched to cylindrical coordinates. So here, once we change, our x is still r cosine theta, which we had on the previous page, and our y is r sine theta. And then f2 is a function of r cosine theta and r sine theta. And then again, instead of f of x, y, z, our function in the integrand is f of r cosine theta, comma r sine theta, but z is still the same when we switch. And then just like whenever you did a double integral in polar coordinates, when you do cylindrical coordinates, you're going to have an additional r in your integrand. And then these are z values. Those are z values, so that's dz. These are r values, so that's dr. And these are thetas, so that's d theta. And that's how we would set up triple integral in cylindrical coordinates. All right, so let's look at an example from the textbook. So we're going to start on page 943. And we're going to do number 1. Number 1 says in exercise 1 through 8, write the equation in cylindrical coordinates and sketch its graph. All right, and they give us y equals -4. So they want us to write this in cylindrical coordinates and sketch its graph. And remember, we're working in 3 dimensions. So this is going to be a plane in 3 dimensions. And we're going to sketch the graph first because it's a lot more natural to sketch something from rectangular coordinates than it is from cylindrical coordinates, because we're familiar with this. So we have our set of coordinate axes, and then we're just sketching the plane y equals -4, which means that x and z take on every value. So we'll go back -4 units, say right there, and sketch a plane. So that will be the plane y equals -4. So now let's look at this plane in the equation of this plane, in cylindrical coordinates. So in cylindrical coordinates, when you have y, that's the same as r sine theta, same as from polar coordinates. So this is just r times sine of theta equals -4. And it's much easier to figure out the sketch from this than it is from that, because remember, to figure this out, we would have to use that picture that I gave at the very beginning, where we're saying that, and notice here, there's not a restriction put on theta, nor is there a restriction put on r individually, other than their product has to be equal to -4 at all times. So it would mean a matter of looking at all the different radii coming from the origin and all the different thetas, where the product of them is equal to -4. And if you did that, you would trace out this entire plane. But that's a lot harder to figure out here than it is from right there. All right, so I'll stop this video here, and then in the next video we'll actually do some triple integral problems. But I want to make sure we did one where we're just looking at conversion from rectangular to cylindrical, or vice versa.